welcome to the inaugural annual lecture on Energy and the Environment. Today we have a real special treat. Our speaker is Srinivasa from Srini, as he's known to many of us. He's currently the Abdul Salam Professor and Director of the International Center for Theoretical Physics in Trieste, in Italy. Srini is an internationally renowned authority in fluid mechanics, applied physics, and applied mathematics. He was educated in India, Australia, got his PhD at Johns Hopkins, and then he joined the faculty at Yale, where he rose through the ranks to become the Harold Shield Professor in 1988. And he's held joint appointments in mechanical engineering, physics, applied physics, and mathematics. Oh, I locked everyone out, sorry. He moved to the University of Maryland in 2002, where he was a distinguished university professor in the Institute for Physical Science and Technology, of which he was also the director, and a faculty member in physics and mechanical engineering. He's really won a very large number of awards, which I won't give you all because it will take most of the lecture. I'll just summarize by saying that he served as editor or associate editor of several scientific journals and delivered numerous main lectures and held various administrative positions. Among his awards, he's received the Buckle Laporte Award and the Nicholson Medal for Human Outreach from the American Physical Society, the 2002 Medal and Lecture in Engineering Sciences from the Third World Academy of Science, the International Prize and Modesto Panetti and Carlo Ferrari Gold Medal from the Accademia delle Scienze di Torino, and the Zakir Hussain Award of the Indian Society of Applied and Industrial Mathematics. He's a member of several academies, including the American Academy of Arts and Sciences, the U.S. National Academy of Engineering, U.S. National Academy of Sciences, the Indian Academy of Sciences, and the Indian National Science Academy. You have to tell us the difference between those two. And the Academy of Science for Developing Countries, and the African Academy of Sciences. Today he's going to talk to us about a topic that has been dear to his heart throughout his career, namely mixing. Srini, it's a pleasure to have you here.
Thanks, Pablo. The talk will go downhill from here on, of course. I already downgraded the title as to some notes on mixing instead of saying mixing altogether. The work I am going to present would involve not only some measurements in the wind tunnels that I made some years ago, but also in particle using laser-induced fluorescence and PIV images, jets like this from which we constructed dissipation fields. And more recently, the work I have been doing with these three colleagues, P.K. Young, Diego Donzis, and Jörg Schumacher, on computational problems related to mixing. And to establish my respectability, I cite for you a number of papers we just wrote in the last few years, and I'm going to extract things from there. So that's my goal for today. Why did I emphasize a bit on computations? If you look at the time axis here, 1940 to 2010 or thereabouts, and plot the floating point operations per second, you can see that around the time I was born, it was only 100 floating point operations. But now we are talking about petaflop machines, which will be soon in existence. So in fact, computing power has really increased tremendously, like almost nothing else. The only other graph that I know can compare with this is the brightness of synchrotron radiation machines. So given this increase in power, we have begun to wonder whether some of the problems of turbulence can be addressed a little better. And on this little line here is an average of the size of the box, a three-dimensional box in which computations have been done. As you can see, 4096 cube calculation was done on the Earth simulator, and roughly this Reynolds number, this so-called microscale Reynolds number, is about 1,000 or so. That means the real Reynolds number, which is the square of that, is about 1,000,000. So you are getting into a regime where things become realistic and you can extract a lot of useful information. So that would be one of the reasons why I emphasize a bit on computations in this talk today. The mixing problems, there are many different types. I at least can identify 3 of them. Those that are accompanied by changes in composition, density, enthalpy, pressure, etc. So if you have combustion or detonation or supernovae, for instance, mixing is at the back of the changes that happen, but that does not tell you a lot about, it does not tell you everything about the dynamics. The velocity itself will depend upon all the combustion processes and the supernovae process and so on. Then there is the other category where there are fluids of different densities mix, and they have a large influence on velocity, but no new products are formed, no enthalpy production, no pressure changes. And this occurs in, let's say, thermal convection and Rayleigh-Terrell instability. In fact, I gave 2 talks very recently at Princeton, and I had to make up a 3rd talk all in the span of a few months. So I had to do this instead of giving the same talk again. Now, that talk was on thermal convection, for instance. Then there is the 3rd variety of mixing, where certain components, non-reacting species, can mix together, but when they mix, no density changes are produced and no dynamics is affected by the mixing process. The dynamics will do all the details of mixing, but the mixing itself does not have a back reaction on the dynamics, and that's why it is called passive. And scalars, because you are talking about species which have no vectorial properties. And this is the title that I choose for my presentation today. And this passive scalar mixing, while it will not explain whatever is happening in these two classes, is at the basic is a basic phenomenon in these two. And if you know everything about this, you can at least say a little bit about what is happening here. And this is therefore a kind of textbook example of a mixing problem, and that's what I want to focus on today. So a typical example would be, for instance, if you have a turbulent domain in which you put a spherical dye object, for instance, with concentration. This is a planar cross-section of a dye, let's say. In the middle, you have large concentration. As you move towards the edges, the concentration decreases, so you might have a Gaussian distribution here. And then with time, don't worry about these units, you can see how these elements are twisted and folded by the velocity field in which it is embedded and eventually become something like this. This is an example of the simulations, but actually in 1959, Corsin had drawn this schematic, which is not all that different in some general sense. I don't think he had any real evidence to go for drawing this, but he had enough intuition to think that it was something like this. Now, everyone knows that such problems are governed by advection diffusion equation, where theta is the concentration of the tracer, so it's the time rate of change of the tracer concentration here, advected by this velocity and diffused by this diffusion coefficient. So that's the problem you want to solve with the boundary conditions and everything. And of course, just for curiosity, the corresponding Langevin equation is x dot is this is drift term due to this velocity, and then you have the noise term, which is this white noise here, and the diffusion coefficient here. So sometimes it is convenient to do the Langevin version rather than go through the PDE written at the top. Now, the problem, of course, is very simple to solve if u is very simple. Of course, if u is very simple, as you for instance constant, Einstein worked out what the result was, and you have the classical diffusion equation. And of course, if u is, let's say, very simple, like a periodic in 2 dimensions, a lot about it is known, and you have the hyperbolic points and twist and folding and so on. And you know a lot about what happens in mixing. But if it is three-dimensional and u, this velocity, the advection velocity, is a turbulent one in 3 dimensions, there are not many results that are known. Not many results meaning not many fundamentally basic results, theoretical results. But that's what I want to consider, and I want to at least bring you to a point where something analogous to a good solution is known to the problem in some limited aspect. Now, how the problem will evolve will depend upon the nature of the velocity that is advecting it and the dye field that you put into it. Therefore, let's consider a few things to build up our intuition a little bit. I want to consider, first of all, a velocity field, a turbulent velocity field that is homogeneous and decaying in time. So you can imagine that you have a container, and you shake the container in some fashion, and you have a turbulent field, and if you put it on the desk, it will die away in time. And it is known that empirically, there is no real solution to the problem. Empirically, it is known that it will decay like minus 1.2 power of time, and the length scale will grow at some power of this. Now imagine, after you set up this turbulence, you set up striations of heat or some dye or something like that. You can imagine putting lots of wires there and heating them up or something analogous. And you want to know how this scalar, that is the fluctuations in temperature that are produced by virtue of folding and twisting of these scalar elements that are introduced by these wires, how will that decay? That's the question. In fact, the question is whether, like here, where the unique exponent, independent of how exactly you produce the velocity field, more or less, will this exponent be a universal one, or will it not be a universal one? I don't know what your intuition actually is, but I give you an answer that it is not really universal. It depends upon m is a variable. I don't know why I wrote it twice. And it depends upon the initial conditions. That is to say, how you put your scalars, how you into the stream will determine how the thing will decay. And in fact, you can make many measurements, and this is a cumulative summary of this. This exponent m is plotted here against the ratio of the two length scales. This is the length scale for the velocity field, and this is the length scale for the scalar field. So you have to imagine that if I have striations in which I put the heat, for instance, there's a length scale involved in how I put in there, and that length scale, its relation to the length scale of turbulence itself, will determine how this exponent changes. This diagram particularly can be found here, but the data are from these two papers. It's not very hard to understand why this non-uniqueness might exist. I will give you a very simple version of this. You have a question?
There's an Enoch Durbin in our lives. I wonder if it was that Durbin.
No, this Durbin used to be at Stanford. It's the same one?
It's Enoch's son.
Ah, okay. I didn't know that. Okay, so now I know something more than I did before. So let me give you a very simple version of why it might be like this. Let's say I have isotherms, that is to say lines of constant temperature, and there is a length scale associated with that, which is L subscript theta. And now this is going to be distorted by the velocity field in which I am going to embed these things. And of course, if the velocity field has a small length scale compared to this L theta, then these isotherms will sort of have very large, many oscillations of small scale. And here, in a very incomplete way, I show this, where the length scale of this, which may be related to these large and rapid oscillations here, is imposed, is really doing the mixing of these isotherms, and therefore the isotherms which were sort of flat like this may assume some shape like this, with oscillations that are rapid compared to this L theta. On the other hand, if you can imagine a different situation where the isotherms are closer together, so L theta is small compared to the velocity field, which has a large length scale here, for instance, then the oscillations will actually, these isotherms will assume a shape like this. And you can imagine that the decay of this and the decay of this will be quite different, because this is put in at a different point in spectral space compared to this. And therefore, depending upon this ratio, you can imagine that the decay will be faster or slower, and that is essentially Paul Durbin's graph. So let's look at some more cases and see if we can have a better intuition. Let's say instead of the velocity field decaying, I maintain it stationary. I can maintain it stationary by a number of ways. For example, I can put in a random forcing. So some wave numbers in the low wave number range can be adjusted, so energy is constantly put into it in order to balance the dissipation of energy that takes place. And the scalar field could decay. That is, I could put in these pulses of heat and then see what happens to the scalar. So that is one case. And this case has not been studied all that much. But what we know is that if you actually have a very non-Gaussian distribution of the scalar, for instance, it may be two delta functions, one at t equal to 0 and one at t equals t naught, for instance. In time, this distribution becomes a Gaussian. So the two things, you can imagine that this would be true. You have a 0 temperature and some finite temperature. With mixing, eventually everything comes down to t by 2, and it will be centered around t by 2 as a Gaussian distribution. That is what is known. You can imagine that the velocity field might be decaying, but the scalar field is maintained stationary. But this is a very difficult case actually to do, and very complicated in practice actually. So I will not talk about this. But you can imagine more importantly, and this is what is quite practical, the velocity and the scalar fields are both stationary. So I not only shake the box and leave it on the desk, but I continue to shake it. I continue to shake it in such a way that the energy I am putting in just balances the amount of energy that is dissipated. And similarly for the scalar, you know that the scalar is going to be eventually mixed and everything becomes homogeneous. But on the other hand, if I keep injecting more and more scalar at some length scale, I can maintain the fluctuations forever. So now, of course, the question is whether the details of these two fields depend upon how I sustain these fields, whether I do it by having a mean gradient or whether I have random forcing. That is to say, in the advection diffusion equation, I have instead of the usual boundary conditions, I put in a term which adds energy at some very low wave numbers. In fact, it turns out that the results are very similar. Some results are very similar. For instance, here I give you some moments of the distribution. One color here represents one of these, one type of forcing. The other color represents the other. You see that they vary, but they track each other very faithfully, more or less. And similarly here. So essentially for the distribution of the probability density of these fluctuations, it does not seem to matter how I maintain the fields. On the other hand, the probability density itself will depend upon how you force. In fact, there are experiments where the probability density is plotted here, the temperature is plotted here, and the log of the probability is here rather than the probability itself. Therefore, the Gaussian distribution is a parabola, and an exponential would be a straight line. You see that the distributions here are exponential, at least if you go outside the core, whereas here they are essentially entirely Gaussian. So in fact, it is not at all clear at the present moment as to what details here matter for this distribution. It's such an amazing thing. These are very basically different things, but we do not know what kind of details matter. And you might imagine again, as before, whether the initial length scale ratio will matter, but this has not been figured out at all. And one doesn't know whether this is enough in order to give you this distribution or this distribution, but this is an ongoing work. So it is amazing that very basic things like this are not known about this. But what is known, however, is that the large-scale features like the distribution of probability and the rate of decay of turbulence, the scalar fluctuations, They depend upon details of forcing, as I have actually shown already, initial conditions, and perhaps the geometry about how you introduce these things. Therefore, it's clear that every flow has to be studied on its own merit when it comes to these aspects. Only some of these features are understood well at the moment, and many of them are simply not understood at all. However, the question would be, if the large-scale features are non-universal, and therefore every problem has to be studied on its own merit, which is putting fluid dynamics in the category of chemistry or something like that, for instance, where every chemical has its own merit and you have to study it. And the question is, are small scales universal? So you sort of bring it back in some sense to, within quotation marks, physics, sort as a problem in physics, for instance. So that's the question that I would like to discuss for the next few, I don't know, sometimes, let's say. Okay, in order to answer this, I have to perhaps remind you of various parameters and scales involved here. This is the Reynolds number, which everybody knows about. This is some measure of the velocity fluctuations. This is some measure of the length scale and the viscosity. And usually for these problems, this is a very large number. As I said, could be 1,000 to million or something like that. And then this is the large length scale in the problem. And also perhaps you know that the measure of the small length scale in the problem is this eta. And it's the smallest length scale, so to speak, nominally, because if you make a Reynolds number out of this length scale and a velocity characteristic of that, that is always 1. So in fact, you have a phenomenon where the range of scales from L, where you somehow think of it related to the container and how you really create the flow, to a very small scale whose Reynolds number is of order unity, and in between you have a very large range of scales. So this is a problem typical of very multi-scales in the phenomenon. And then you have two diffusivities. One is the diffusivity related to vorticity or momentum, and then here you have the diffusivity of the scalar. So the ratio of the two is the so-called Schmidt number. And this number could be very small or very large or of order unity. If the scalar you are considering is temperature, this is unity. Or if you are talking about gases in general, it is unity. If you are talking about liquids, you know that the diffusivity of things you put into liquids is much smaller, so the Schmidt number is very large, of the order 1,000 or thereabouts. And if you are talking about, let's say, the phenomenon of conduction in the sun, for instance, and there the Schmidt number could be very small, of the order 10 power minus 3. So you might be interested in phenomena that go from very small to very large values. And so that is one of the things we should like to keep in mind. Now, this is what is known traditionally. So I have the large length scale and I have the small length scale, and in between the two. And in between I have this so-called inertial range with 5/3 power with a coefficient that is known to be 0.5. This is a paper I wrote some years ago. And another one for the scalar. Similarly, you put in these fluctuations at scale L, and then that too will generate many scales, because these isotherms are twisted and folded and so on and so forth. And that too has a 5/3 power law with a coefficient sitting in front, which is different from what is here. So that is roughly what is known. And one of the other important things that I should mention is that the rate at which the energy goes from here to here is also the rate at which the energy is dissipated here. So essentially, energy you put in here is dissipated here. It only changes the dynamics of the scales in between a little bit qualitatively. And therefore, the amount of energy that is dissipated here, although the dissipation mechanism is viscosity, is independent of viscosity, because it's all coming from there. And in fact, this is not a very obvious point, and that's called the dissipative anomaly. And you can see it here. The energy dissipation becomes independent of Reynolds number after a certain Reynolds number. That is, when the viscosity is small enough, the magnitude of viscosity does not matter. That is one of the features that distinguishes turbulent from any number of other random phenomena. And here for the scalar variance, similarly, after a certain Reynolds number or Peclet number here, the rate at which the scalar variance gets smeared out by the diffusion is also independent of the diffusion coefficient. Now let's talk about the case of large Schmidt number, which is of great interest because this involves mixing of dye, let us say, in liquids. So you have a jet or something like that, and you put in a bit of dye, and this dye is dispersed in the medium, and the Schmidt number is of order 1000. And then what is it that is known? Here, for instance, is a picture of the simulations with different Schmidt numbers 1, 3, and 8. It's essentially the same thing. When the Schmidt number is larger, as you can see, more and more striations are formed at smaller and smaller scales. So this is essentially the effect of the Schmidt number. And basically what you have then is that you not only have scales going from L to eta, but also all the way going from eta to eta b, B for Batchelor, who studied this thing here. And in between, and this process of stretching like you have here will go on until the diffusivity is such that the gradients created at these very large gradients created at these small scales become effective through this very small diffusivity. So the smaller the diffusivity, the lower and lower down in scales you go, or larger the Schmidt number, the lower and lower down you go. So what is known about this? Essentially here everything is known as before, what I said before in the previous diagram. But here Batchelor's prediction is that it goes, the spectrum goes like -1 power of the wave number, and so this would be Q, a constant, would be of order unity. In fact, what do we know about this? First, before I tell you what we know about this, I have to say that we would like to solve some of the issues or understand some of these issues computationally, because experimentally there are issues that have not been resolved, and I can tell you about this. But there is a problem with computations. The number of grid points that you need will go like the, or let's say the computational power needed, will go like the third power of the Reynolds number and the second power of the Schmidt number. So if you have a Schmidt number of order 1000 and a Reynolds number of order 1000, you can see that this will be a very immense calculation to make. And therefore, in whatever I have to show you now, at least I have to show you that I have resolved things well. And I would maybe take a few minutes to show you that this can be done in the modern computers. And here, for instance, I show you a picture of the scalar field with the normal resolution, the resolution that everybody has been doing in the past, and what we believe has to be done, which is at least here 4 times larger. And the scalar fields are not that different. You see, they look essentially the same. However, if you take the scalar dissipation field, that is the rate at which the scalar gets smeared out, related to the gradients in this, you can see that there are some details that you can see better here are actually fudged here, especially when the scalar dissipation is small. You can see the nice structure that you have here, which is very conspicuous, is essentially missing. So you have to resolve things better and well. And one other thing I can show you is that if you take a dissipation of a certain magnitude, if you resolve them according to the standard fashion, you will get the dissipation field that is like that. But if you do it the way I think it has to be done, with the right amount of resolution, you will see structures like this. And therefore, among the things we have done is to make sure that the resolution is adequate. And how you do that is, if you resolve them finer and finer, at some point everything will be Taylor expandable, even though the fluctuations may be very very rapid and very rough. Then if you go to small enough grid size, discretization becomes correct, so to speak. And I have plotted the results for some moments in such coordinates that will tell you show you that it must be flat by Taylor expansion. And in fact, you can see that the data that extend up to there, in fact, fall on the right flat lines. And this is our theoretical attempt to understand what is the minimum resolution that is required. So We have therefore gone well past the minimum resolution that is required in order to resolve this. Even high order moments like this, just barely making it, for instance, here, and you can get a dissipation field like this, which looks very pretty, but one hopes is correct. Now, the resolution is given in these units, the Reynolds number here, the Schmidt number here, but these are for experts who want to have details of this, but I will not go into this now. Now, another thing you can do is the scalar dissipation field. You can expand this here, and this is the grid size, and this is, I'm sorry, this is a wrong color. So this one is the smallest velocity scale, and this is the smallest scalar scale, and in fact we have gone well below that. And even in the cases where the dissipation is small, which is shown by the purple as opposed to red where the dissipation is large, you can still again see all of them resolved reasonably well. So now, from all this exercise, what do we learn? So let me talk about this Batchelor regime that is between the Kolmogorov scale eta and the Batchelor scale eta b. And as I said, the expectation is that you would have a -1 power law. But let's see what the experiments show. 1963, Carl Gibson made these very nice experiments, and he thought he saw -1 power. And many years later, we did some, and we thought we saw the -1 power law. And of course, there are skeptics here whom I have listed, and they say, well, there is no such thing. And in simulations, Holzer and Sigia made the simulations, and they thought they saw -1 power law. Now, actually, what you see is that if you try to fit a -1 power law for a certain region, it's this region is -1 because I have normalized by -1 power. So -1 power means flat line. Even though the Schmidt number is about 1,000, that means the scale separation is quite large, you will still not be able to see decades and decades of flat region. And therefore, the right thing to do is not to simply look at this region here and try to see whether this is flat or not, which lies in the eyes of the beholder to some degree. But you want to fit a theoretical attempt to the entire spectrum on small scales. And that is, in fact, what we have done here. And you see, there is a theory due to Batchelor, and there is a slightly modified theory of Kreiknen. And you see that theory fits these data points extremely well. So this one here is Kreiknen, this is Batchelor. It shows that the improvement that Kreiknen had actually is correct. And here is another set of data, several sets of data, giving you essentially a -1 power, but the entire thing here can be represented by this formula. So what about this coefficient Q? I'm sorry about the quality of this graph. But Q changes with Schmidt number somewhat modestly, and beyond the Schmidt number of order 10 or so, it remains constant of order 5. Batchelor assumed that it is a constant of order 1, and I think he was essentially right. So now let us discuss a little bit about what happens to the dissipative anomaly. You remember that the amount of the rate at which the scalar gradients are smeared out by the diffusion coefficient, I said, is independent of the Reynolds number or Peclet number for Schmidt number of order unity, and this is this one of these lines. But different Schmidt numbers do seem to want to go to constant numbers, but these numbers are all different. This is something which no one understands how to interpret and how to explain theoretically. And another thing that we know about is that if you generate turbulence, generate the scalar field by means of a gradient, which means the large scale is no longer homogeneous and isotropic but has some orientation to it, then even the small scale retains that orientation. And this is just a measure of that orientation as a function of the Reynolds number. Theoretically, what you would like to see is that this number to come down as the Reynolds number goes up. But in fact, you cannot tell. You cannot tell from this data whether it is going like this or it is going like this. This is the data, experimental data I collected some years ago. But computationally, now we know that actually it goes down like this. So we are beginning to understand the sorts of things that...
Experimental data,
yeah.
It is some kind of distribution of the data. What do you mean is
this is just the skewness of the distribution of the gradient. So
there's different data for the same conditions?
these are different data acquired by different people in different experiments, but all of them have the common characteristic that there is a temperature distribution, and you have a mean gradient in temperature and mean gradient in velocity. In fact, the sign of this depends upon the product of the signs of the gradient in velocity and gradient in temperature, but I've just plotted the absolute magnitude. So these were taken in some of them. These are atmospheric data just above the ocean, for instance. At one time, I did some measurements on the ocean as well. Now, so that is getting resolved already, and I want to also show you what the effect of the Schmidt number is on this anisotropy. And here is the same picture you saw before. And you can see what happens if I increase the Schmidt number. The distribution of the gradient, which was like this for low Schmidt number, as the Schmidt number goes up to 64, the left-hand part that is related to negative gradients just goes up. And this is the one that I told you earlier was very sensitive to resolution and so on. And eventually you can see things becoming more or less symmetric. And I have here a measure of the distribution of this anisotropy, and it goes down as I go up in Schmidt number. So essentially, Schmidt number increase, and here is the third moment that I showed you earlier, which was about a unity for low Schmidt number, but then goes down with the high Schmidt number. And then this is of great interest to practical people, the effective diffusivity of the scalar. There is molecular diffusivity on the one hand, but because the stretching due to turbulence increases the surface area of the scalar field, and there is a lot more area across which diffusion can occur, the effective diffusivity will be much, much, much larger than the molecular diffusivity. And the ratio will, of course, depend upon how much stretching you can do before things quench off, for instance. Now, similarly, there is the effective viscosity, and you might take the ratio of the two and ask what happens to the so-called effective Prandtl number or effective Schmidt number. This is a number of great practical interest, and it turns out it depends upon the Schmidt number. These are various realizations, and if you actually average them out, the curve looks much smoother, which I didn't do. It goes down logarithmically, and in fact there is a little bit of theoretical understanding of where the logarithm comes from. The logarithm comes from the fact that the spectral density, if it has a k to the power minus 1 power, if you integrate it to get the energy, so to speak, under that, k to the power minus 1 gives you a log k, and that is really where the logarithmic distribution comes from. And the last point that I want to make in the next few minutes or so I have is this so-called intermittency. Now, what is done here is you have a box in which the velocity field is maintained stationary and turbulent, and in which the scalar field also is maintained stationary, and now the mixing process is going on. And at any point in time, which is statistically the same as any other point, what you do is you take different planes in that box, and you plot on each of those planes how the dissipation of the scalar, that is the rate at which the gradients are being smeared out by the diffusion, looks like. You can see that this is the color code. You can see that most of the time, most of the places, not much activity is happening, but there are some places where there is enormous activity. That is to say, the dissipation or the smearing effect is not uniformly distributed in space, but it is quite sporadic like this, or what is in the jargon known as intermittent. Now, this is not very surprising in some sense. If you look at pictures of the sort I showed you already, the areas of large gradients are actually distributed in some sporadic fashion, and not more or less uniformly spread out like a Gaussian or something like that. And now, what is the impact of this? It appears to me that this has extremely important consequences. In the formal theory that people have done all the things I have showed you before, it's assumed that these things will fluctuate, but they will not fluctuate so rapidly and so randomly, but they are sort of mellow fluctuations, so to speak. Let's say like the temperature changes on a very nice summer day or something like that, it doesn't change all that much. But if it on some other days, wintry days, things might change very rapidly. Now, in fact, if you take the gradient field from which this is coming and look at the distributions, you see how much fat tails they have in comparison with Gaussian, which is a parabola here because I plotted the logarithm. You see, if you want to ask yourself, compared to what a Gaussian value is, this magnitude, how much more probable is it compared to this? You can see how many orders of magnitude it is. It's probably of the order a million times larger. So million times larger at this value. But if I go to 10 standard deviations, I have not just million, it is a billion-fold larger. If I go to 20 standard deviations, it is just astronomically large number. So this obviously will have some effect, and I want to say what is one of the important consequences. I have some technical details here, but essentially I will tell you these things relatively simply. Traditionally, what people have defined is that Kolmogorov defined a scale called the Kolmogorov scale, naturally. Now, he defined it as nu cube over average value of the dissipation to the power quarter. The average value is perfectly fine. If things are varying only smoothly, an average will tell you a lot about the quantity in question. But if the things are oscillating rather wildly, if you take the average value, it actually lies somewhere in the noise level and it doesn't tell you very much at all. So you want to go to next order moment, maybe the variance, maybe third order, maybe fourth order, and so on and so forth. Now, that is not my point here. My point really is that if instead of defining a length scale through the average value, I take the local value of the dissipation and define a local value, local scale, that scale is going to be quite different from the average value. And that's really the theme that appears everywhere all the time. For example, I can define a diffusion time which is related to how fast a gradient of the scale eta b is smeared out by this diffusivity kappa, and that would be the standard definition. But in reality, I should have eta b squared divided by kappa before averaging, and then if I average it, I have to do eta b squared average rather than eta b average squared. You see, so that's the basic idea. And what you do is you look at the local scales and look at the distribution of these scales. In fact, here is how you can measure these scales, and you find something extremely interesting. So this is the dissipation scale divided by the average value. Logarithm to base 10 is plotted here, and this is the probability density of this quantity here. In fact, this is a relatively wide distribution. This here is the average value, more or less eta or eta naught is unity, so logarithm is 0. So it is distributed very widely. So what it means is that the so-called small scales, supposedly one fixed value like Kolmogorov thought, is really not one fixed value, but is distributed around a certain value. Now this has some important consequences, and I don't know. This is all has a lot of stuff in it, but basically, what it means is that if you are resolving your problem, you are not going to do the problem right if you resolve it only according to the average length, because there are smaller scales than the average value and there are larger scales than the average value. So if you want to do the problem right, you have at least got to resolve the smallest possible scale, and you can do a theory for the smallest possible scale, which I don't know. I have it here, for instance, in this paper. And the main point is that, as I said, the diffusion time is not is actually this. You have to take eta b squared and average rather than eta b squared as was traditionally done. And if you do that from the distribution, you can actually show that the real diffusion time is about 10 times larger than the usual time that people have talked about. And this 10 is a large enough number that it will make a big difference for interpreting a lot of data. For instance, you can take an eddy diffusivity time, that is the diffusivity time related to how things smeared out on the large scale, compared to the molecular diffusion time, and there is this formula which is saying Reynolds number to the power half, but if I take that factor 10 into account, it is 100-fold smaller. And because of that, you can see that This ratio is of order unity if the Reynolds number is of order 10 power 4 or so, and it becomes larger and larger only with higher Reynolds number than this. So people like Paul Dimotakis had actually noticed that around this Reynolds number there is a transition that occurs. We called it a mixing transition. And what happens is sort of clear, it seems to me. There was no explanation in Paul's work. But what happens is that below this Reynolds number, or of that order, you cannot separate eddy diffusivity from molecular diffusivity. They are both of the same order, whereas only much higher Reynolds numbers do these quantities separate out. That means you have really the effect of turbulence. And it also sort of related to this so-called short circuit in cascades, which I will not bother about. So now I come to my last point, which is that turbulence nears a final answer. This is a statement I picked from Uriel Frisch's work, and I want to tell you why he is so excited about it. And this is his excitement. His excitement is that normally, if you take the nth order moment of the difference in scalar over a size r, there are some exponents associated with that. And if you follow the standard theory, nth order moment is equal to n by 3. But if you have the so-called anomalous scaling, then zeta n is not n by 3, and that means to say it is actually a concave function. So 2 zeta n is greater than zeta 2n. So the exponent corresponding to the nth moment multiplied by 2 is greater than the exponent corresponding to 2nth moment. So this is the idea. And of course, why should one care about this anomalous exponent? It's important because if people are interested in scaling, especially if you come from critical scaling, then you know that this is actually a totally new paradigm for critical scaling. And of course, anytime you are interested in moments, like I said, for instance, the second moment of the scale as opposed to the first moment and things like that, then it matters that the nth moment is not the same as the second order moment to the power n by 2 I should have had. So that's the importance of this. And so at least people who come from the critical phenomena background think that if you can somehow compute this or show that this is true, you have solved the problem in some sense. And when he said turbulence nears a final answer, this was already 10 years ago. I should have really said turbulence has a final answer now, but I'm afraid I cannot. At least you will see whether you will agree with this or not. It's up to you. So what is the problem that was solved? The problem that was solved, which has some general interest, this is the advection diffusion equation. And then this V here, I called it U earlier. I'm sorry I changed the notation to V. This is the one usually obtained by solving the Navier-Stokes equations. That's the one that advects the temperature field. What Kreikkinen thought was, since that is a very difficult problem, let's replace this by a surrogate velocity field such that its spatial correlation between two positions x and y is really going like some power in the separation distance. And a special point of that is the Richardson law of diffusion for this particular value of gamma. But the two fields in two instants of time are uncoupled from each other. So imagine I have a field which, let's call it the surrogate velocity field, which is fluctuating like this. It has certain spatial length scale which vanishes like a power law, but its temporal correlation is essentially 0. That is to say, the field is like this now, and the next instant it is doing something else altogether. The two are uncorrelated with each other. This is not like the velocity field in reality, but that's the model he chose. For this problem, because the velocity field does not persist, you can have many simplifications in the problem, and you can actually solve the data. And here is the real turbulence field, scalar field, and here is the scalar field computed from this model, for instance, for one particular value of gamma. Now the interesting thing is that if you take the probability density of the gradients in the real field, and this is how one obtains, this is the data here, and the model for which the one I showed you earlier has a solution which depends upon a certain parameter which varies between these two numbers. You see, these two are the bounds for this, and perhaps something in between is entirely possible. So it's actually quite surprising that a model that doesn't seem to have any reality to it because it's so rapidly varying in time somehow gives such an extraordinary detailed quantity more or less right. And in fact, it turns out that you can also compute these exponents. This here is 2 zeta 2 minus zeta 4, and for normal scaling it would be 0. But here, as a function of that parameter gamma, there is a theory for gamma going to 0. There is a theory gamma going to 2. And the theories seem to be agreeing with the numerical simulations of the problem. And this is a finite number. Therefore, you have solved a problem, at least a model problem, for which anomalous scaling is real, independent of even the simplicity of the velocity field. So that was the excitement that Frisch had, and you have to decide for yourself whether it is such an important problem and therefore deserves the claim that the problem has more or less been solved or not. That depends upon your test. And the main conclusion from here that they draw is that the mixing process itself imprints large-scale features independent of the velocity field, because the velocity field is no longer Navier-Stokes, but it has the characteristics of the Navier-Stokes velocity. But of course, this cannot be entirely true. Everybody who swims in ocean will know that large-scale features really are somehow related to how things mix and move about. But for certain features, it seems to be the correct interpretation. So here is a summary of the major points I have discussed with you today. One is that the large-scale features of the scalar mixing depend upon initial and boundary conditions, and only some of them are understood relatively well. For instance, I showed you how the exponent changes as the exponent of the decay changes as a function of the length scale ratio. There is some understanding of such issues. Some classical predictions of the past have been confirmed, for example, relating to -1 power, and we have the spectral constant. Somewhere here ought to be a bracket. And the effects of molecular Schmidt number have been determined by means of very fine resolution, and these are some of the problems I looked at. Predictions from the Kreiknen model have been assessed. This is the one related to the PDF of the gradient field. And as one effect of intermittency, the existence of sub-Kolmogorov and sub-Batchelor scales have been established, and these effects are important to explain mixing transition and short circuit in cascades and things like that. So after many years of working on this at some level or the other, this has been a problem at the back of my mind for many years. We have made tentative progress in some areas, reasonable progress in some others, and I imagine if you give me any particular problem, I can probably have some idea of how to approach the thing and how to assess the result, so to speak. I think time has come when you can say some qualitative understanding of what is happening about turbulent mixing. Thank you very much.
Time for questions?
Do you think that as our computer power increases and we can simulate turbulence to higher and higher resolution, we will necessarily understand it better? And do we even need to understand it if we can simulate it?
Now, of course, it's a question of what understanding means, and you can do more things for sure. I have to say that as the Reynolds number goes up, the scale you have to resolve becomes smaller and smaller compared to the traditionally held value of the Kolmogorov scale. So you will not gain as much in computing with computing power as one had hoped. Therefore, the gains will be smaller. Nevertheless, gains will be made. I once made an estimate of what is the ultimate that is possible. Let's say you have computing elements which are the size of molecules, and it cannot go any further, any smaller. And then let us say the speed of communication from one element to the other is like speed of light, which is the limiting factor. And then you say, I want to build a computer in this room, which is a reasonable one. Now you can ask, how many floating point operations can you perform, and how much of a problem in turbulence you can solve. You can actually solve a fairly big problem, but it will still not be of the order of geophysical flows. But it can be, many engineering flows can be solved by such a machine if one were to conceive. Then the question is, what is understanding? Understanding eventually is something that you can bring it down to something simple. If you don't see simplicity in a very large, complex thing, and you say, oh, it's very complex, then you have understood nothing. So how to bring down the simplicity from this large measure of computing is going to be a big problem. And you need a theoretical underpinning in order to at least allow you to think about these complex databases. And that's why simple theories like this are really very important. So my feeling is that if you understand some very elementary aspects of the problem, eventually, anytime you want a special problem to be solved within quotation marks, you basically have to compute it. And I think if you get to a stage where you understand the essentials, but then anytime you are confronted with a particular problem, you can compute it away, I think the problem is finished as far as I'm concerned. I really think that's the way I would see it.
I think you mentioned at the beginning that you can apply this theory and this calculations to look on turbulence on sun. It is correct what I understood you in the beginning when you mentioned it can be applied to sun? Or
I was giving sun as an example of a very small Schmidt number, but the one about which I feel that I can say something about is convection in the sun, the outer part of the sun.
Turbulence and a lot of, say, solar wind, say solar flares
Yes.
are very much related, according to people, to turbulence.
They are, but there is a magnetic field which is very important there. So it is going to be modified by the magnetic field. So the kind of simple things that I said without any body forces present can only give you a qualitative answer, but not the correct answer. Now, where I feel we could say something about the sun is that if you take the outer part of the outer shell of the sun, which is where convection is very important because inside it is all radiative, then you can ask what is the Rayleigh number, let us say, corresponding to this, which is the measure of Reynolds number, something like that. Now, my best estimate for it, using for fluid properties, mean free paths and so on, which people have somehow estimated, is it is of the order 10 to the power 22. So it's a huge number. But we can do experiments today going up to 10 to the power 17 in the lab. And so you have still a few decades to go. But if the law is established up to 10 to the power 17, you can presumably extrapolate and get the right answer. So that's how far you can go.
I'm impressed by how difficult the problem is and how it scales up. I wonder if it is easier if you just give up on the continuum and just do 10 to the 26 molecules running around, keep track of it by some Monte Carlo. I mean, it gets to be very, very small. It just doesn't seem like this continuum idea works anyway.
In fact, now people have been using these molecular dynamic simulations, but they can only compute for a millisecond or so because you have so many molecules to consider. And there are some fast processes, for example, Rayleigh-Taylor instability, where even on millisecond things happen very rapidly, but that is the best I know. So your idea is actually is not so out of the blue. People have been doing this, but it is going to be quite difficult to go to realistic time scales. The Bernie Adler in Lawrence Livermore is the one who has been pushing this.
They've been doing that
For many, many years, for decades. Yeah.